Okay, so now the recording is on. I think we can begin. So I think we stopped here last time. You are supposed to prove this. I hope you have proved it. Have you? So we'll start from this point. So before we proceed, we'll just review. I think we had done that yesterday, but we can review it. So this, if G is a group and H is a subgroup of G, we denote the set of all distinct left cosets of H in G by this G and then /H. So this is a /. It is not the vertical, it is not the backslash. The backslash has a different meaning. So you always must be very clear with your notation. This should be a /G /H. That's the notation. So this set is simply the set of all the left cosets of H in G. So we'll look at an example here. If we take D3 to be, we take our example group as D3, and we take this subgroup H of D3, then we had seen earlier that the distinct left cosets of of H in G are these two, H itself, and this second set consisting of B, AB, and A squared B. So these are the two left cosets of H in G. So we can, for simplicity, we label this second left coset as T, and the first one usually is the subgroup itself. We just leave it as H, and therefore we can write this set of all left cosets of H in D3 as a set. It's just made of two elements, that is H and T. So this is a set that is made up of other sets. So the elements in here are sets. So this gives you a set of all distinct left cosets of H in G. So using the same ideas, you can determine the left coset of this subgroup of D3. So you can set up this set, the set of all left cosets of K in D3, where K is this subgroup consisting of just E and B. We saw earlier that this is a cyclic subgroup generated by B. Is that clear? Hello, you can hear me?
Yes.
Yes.
Okay.
Yes.
Good. So here is a theorem. It says the following: let H be a normal subgroup of G. Then we make the following claims. The first one is that the set of all left cosets of H in G is a subgroup, is a group rather, under multiplication of cosets. We shall see how multiplication of cosets work in a short while. But this set, you can define a binary operation on this set. In particular, this multiplication of cosets, and it will be a group. So the next property is this map, which sends G to this group. Remember, we have established that, not really established, we have made the claim that this is a group. We shall establish it shortly. But you have a map from this group to this quotient group, defined by each element is simply mapped to the left coset, determined by the same element. So X is mapped onto XH. So the claim is that this map is a surjective homomorphism and the kernel of this map is just a subgroup H. Now, this only works if H is a normal subgroup. For any other subgroup, you cannot make the same claim. So this is really important. It only works whenever the subgroup is a normal subgroup. Yeah. So we shall prove the first part. We need to check that the set of all left cosets of a normal subgroup forms a group under multiplication of cosets. So to check that it's a group, we must check all the different properties for a group. So the first one is to check closure, then we have associativity, and so on. So since the set of all left cosets of H in G will contain elements that look like this, where A, B, and C are elements of G, so we pick 3 left cosets of H in G. Now, if you multiply the 3 left cosets of H in G, remember we said H is a normal subgroup, and we saw earlier that if you multiply 2 left cosets of a normal subgroup, you end up with another left coset, right? This we saw earlier. But so we have shown that if you multiply 2 left cosets of H, you end up with another left coset of H, and therefore this operation is closed. So when you're multiplying these left cosets, you're just using the group operation, which already is known to be associative. So that group, that operation, that property is inherited. So even for left cosets, the associativity will still hold because it's the same elements. You can easily say that the multiplication of left cosets is associative. So we have shown 2 properties. Now we need to find the identity element in this group, and we test out this left coset, EH, which is just H itself. The left coset of H determined by E is just H itself. And when we multiply it by any other left coset, we realize that the left coset is left intact. So this is actually the identity element. H itself, or the left coset determined by E, is the identity element. And it works on both the left and it also works on the right. So we have shown 3 properties. We have shown closure, it's associative. We have found the identity element. And now we need to find the inverse of left coset. So since we know the identity, to find the inverse, we simply need to find some coset to multiply by our left coset so that we get the identity. We check that if you use, if I have a left coset AH, now the left coset A inverse H turns out to be the inverse, because when I multiply these 2 and use the property that H is a normal subgroup, I can bring this together. I have A inverse H here is equal to H, rather is equal to EH, which is the same as the identity. Remember, the identity is up here. So if I multiply this left coset AH by this left coset determined by the inverse of A, I get the identity element. So what that tells me is that the inverse of this left coset in this group is simply the left coset of H determined by the inverse of A. So we have checked all the 4 properties. The last one, we have just established that every element in this set of all left coset has an inverse, and the inverse is also a left coset of H. So we can conclude that the set of all left cosets is a group under multiplication of cosets. Is there any question? You need to confirm that you can still hear me.
Question.
Yes.
Are left cosets and right cosets equal? Like, let's say
they are not equal, and how you can check if they are equal is to try and compute them. That's where you need to be a curious student. So that question is easily answered by you if you try to compute. It will happen for some. If H is a normal subgroup, we saw that the left coset, I think we did that yesterday. We probably have not spent time on this. If H is a normal subgroup, then the left coset of H determined by X is equal to the right coset of H determined by X. So when H is normal, they are equal.
Oh, okay.
But if H is not normal, this will not happen.
Because the proof of the question you gave us has it applied that theorem.
Yes.
This
So
one.
that's good. If you have actually tried to do it, that's a good sign. It means you are taking your work seriously. So it is not always true that the left coset is equal to the right coset determined by a particular element of a group. But when H is normal, if the subgroup is a normal subgroup, then its left coset determined by a fixed element will be equal to the right coset determined by the same element. What you can do is go back to the examples we have done. We have given examples of normal subgroups. Can you check the left cosets and the right cosets and check that they are equal for normal subgroups? And you should also check that for those that are not normal, the left coset and right coset will not be equal. So we have confirmed we had two things to check. The first thing was to check that this set of all left cosets is a group under multiplication of cosets. We'll do some concrete examples so that you see how this multiplication is done. Now, the second bit is to show that this map is a surjective homomorphism. So where the work is just to check that's a homomorphism. Otherwise, for you to check that it's the surjective part is rather trivial, but we'll see the proof in a minute. So the part two, the map is clearly surjective because if you pick any left coset XH, then its preimage will just be X in G. So every left coset will have a preimage in G, and that makes the map surjective. So now the next bit is to check the kernel. Now I skipped the part that shows this map is a homomorphism. So I think you can check that part. So this proof is not complete because we need to actually show that this map is a homomorphism. Remember, H is normal. So if I get the image of XY, if X and Y are elements of G, the image of XY will be equal to the left coset determined by XY, right? Which is XYH. But since H is normal, I can write it as XH, YH. And that will be the image of X multiplied by the image of Y, which makes the map a homomorphism. So maybe in your own time, you can write out that part, which proves that this map is a homomorphism. So now the kernel of the map will simply be all the elements in G which are mapped onto the identity in this quotient group. So this is usually called a quotient group of G by H. So we want the kernel. We know the identity in the quotient group is just H itself. So we need all elements in G which will be sent to the left coset. So that will be all elements X in G, such that the left coset determined by X is equal to H itself. But we know that if XH is equal to H, then X must be an element in H. So this is an if and only if statement. And I think I had asked you to prove this earlier. Hopefully you have done that. So this means that the kernel must be a subset of H, because X was picked from the kernel, and it satisfies this property. and that it is in H. That means the kernel is contained in H. So if we can prove the reverse inclusion, that is to show that H is contained in the kernel, then we will have confirmed that H is actually equal to the kernel. So let's pick any element in H. If you pick any element in H, then X, the left coset determined by X, will just be equal to H itself. So it means that X will be in the kernel because X is sent to the identity. So that means any element in X will also be in the kernel, and that means means that H is a subset of the kernel. So we have these two inclusions. The kernel is a subset of H, and H is a subset of the kernel, and therefore the two sets must be equal. We conclude that the kernel of this map is simply H. So so we use this result up here, that XH is equal to H if and only if X is an element of H. So you need to prove this result in your own time. Any questions on this? So we do some concrete examples on this. So let's consider our favorite group, the dihedral group of degree 3, with this left subgroup H, the subgroup which is simply, you can still hear me? Everything is too quiet.
Yes, we can hear you.
Yes, sir.
Good. So
Yes.
the left cosets of this subgroup are these two, H itself and this. Okay, that's
Yeah, we
good.
can still hear
And
you.
this left coset, I mean this other coset. So there are two left cosets. We call one of them H, and the other one is just the left coset of H determined by B. Now, how do you multiply the left coset? So if you multiply H by itself, it's simply you multiply elements of H by elements of H, and you will not get anything outside H when you do that. So if you multiply H and H, you will get H itself. So if you want to multiply H and BH, what you simply do is you pick an element from H multiplied by an element in BH. So for instance, you can pick A multiplied by B. And when you do that, you realize there's an element AB, you get AB. You can pick A multiplied by A squared B. What will we get if I multiply A by A squared B?
Get E.
No, that is not true. If I multiply, I have A, then A squared and B. I will have the identity multiplied by B. So I will have B. Yes.
B.
So you will notice the following. If you multiply anything from H and anything from BH, you will still end up with something in BH. So that means, if you, basically what it means, if you multiply H and BH, you will still get BH. So you just pick the distinct elements that you obtain after the multiplication. So anything you pick from here and multiply with something here, you will end up with something, an element in BH. So that product will simply give you BH. You won't get anything different from BH when you multiply H and BH. So this shows you that H actually acts like the identity element when you're doing this multiplication. So if you multiply BH by itself, then because H is a normal subgroup, you can put the B, you can have B squared H. This will be equal to B squared H, because you'll have B, which is B squared H. But you know that the B squared is the identity. This just gives us EH. So BH multiplied by BH will just give us H. So it turns out that BH is its own inverse, because when you multiply BH by itself, you get the identity BH. So we can represent this in a multiplication table below. We have H and BH as our elements, and you see H will be your identity element. And if you multiply BH by itself, you get H. BH by H, you get H, and so on. H and BH will give you BH. So are we to get up to that point? So this gives you an example of a quotient group. So this quotient group of D4 by H is consists of these two left cossets of H in D3, and that's how you do the multiplication.
Excuse me.
Yes.
Now in that last part that we see that H times H is equals to H. That means H is an identity element.
I don't understand your question.
I'm asking that H stands for identity element, that H times H is equals to H.
Well, definitely here we have already established that. I think if you are paying attention, if you say this is a group, H is a normal subgroup, right? So we create the set of all left cossets. So the elements of this group are sets. Each element in this group is a set, and that set is a left cosset of H in G, right? So we already established that the identity will be this H itself, right?
Yeah.
In this group, if G, if H is a normal subgroup, this quotient group will have the identity equal to H itself. So this is already established here. We can just use it in the next when we are using it for any normal subgroup. So this works for any normal subgroup. Does that answer your question?
Yes, it is.
So pay attention to the theorem and learn to be able to move with it to the example. So here we have D3 and we have a normal subgroup. We have set up the quotient group, which consists of these two elements, H and BH. So let's see. Here is some work for you. If you take D4, the dihedral group of degree 4, these are the symmetries of a square. Then we have this as a subgroup, E A squared. So you have a number of tasks to perform here. First one is to show that K is a normal subgroup. Then compute all the left cossets of K. So that means you will have found the quotient group. And then you will write out the multiplication table for the quotient group. Now you will realize that this quotient group will have how many elements? How many distinct left cossets will K have? So the first person to answer will get 50 MB.
4.
Hey, mnangoja pesa tu bwana. But it's correct. Why is it 4?
Because you divide the order of the two groups, the order. So one is 8, which is D4, and the other K is 2.
So you don't say the order of the two groups. You divide the order of the group by the order of the subgroup. That is more appropriate.
Yeah.
Yeah. Because K is, here you are better off thinking of K as a subgroup of D4, not as a group on its own. But it's still a group. It's just that you're better off thinking of it as a subgroup of D4. So this is actually, this K is the cyclic subgroup generated by A squared. A squared is just the 180 degrees rotation anti-clockwise rotation. We saw this earlier, so you can always go back to the video and refresh your memory. So this is work for you to do. You can do it in your own time. So let's look at another example. This time we consider the group Z12. It consists of these 11 elements. 12 elements rather, not 11. And then we pick a subgroup of Z12. So we pick the subgroup of Z12 generated by 3. So it consists of these 4 elements, 0, 3, 6, and 9. So remember here, what is the binary operation in this case?
It's addition.
Which addition? So it's addition modulo 12, right?
Yes.
It's not the normal addition you have for integers. It's addition modulo 12. So we know that Z12 is a commutative group, and therefore any subgroup will be a normal subgroup. Recall that a subgroup of any subgroup of an abelian group will always be normal. I think we gave this example. You were supposed to work out the details to prove that. So let's set out the left cosets of T. One of them is T itself. Now recall that previously we have been written in the examples we have done before, the binary operation is written multiplicatively. So when you write the left coset, you write it as BH here because you assume the binary operation is written multiplicatively. But since in Z12 our binary operation is additive, when writing out the left coset, instead of writing 0t, we write 0 plus t. So it's the same thing, it's just this to denote that our binary operation is additive. So we have the first left coset, which is just t itself, then 1 plus t, which we decide to label s. So s is just a way of writing, so that you don't have to keep writing 1 plus t, we give it a label. There's nothing special about s, you can use any letter that you wish. Then 2 plus t will give us the third coset, which consists of 2, 5, 8, and 11, and we call that left coset R. So we can perform some addition. So this forms the complete set of left cosets of T. How do we know we have found all the left cosets? Anyone? Why did I stop at 2? Why didn't I continue to try the rest? Because we still have other elements. For instance, I could have tried 7, 8, and so on. Why didn't I bother with those? So remember the Lagrange's theorem. The number of left cosets is equal to what? It's simply the index of the subgroup. And the index of the subgroup is simply given by the order of the group divided by the order of the subgroup. So the order of the group here is 12. The order of the subgroup is 4. It has 4 elements. So 12 over 4 will give me 3. So once I find 3 distinct left cosets, I should not bother to look for more because I won't get any more. That's the best I can do. So once you find 3 of them, you know you're done. You will not get any new ones if you used any other elements of Z12 to obtain a left coset. So we can do some, in this case, create the table Now this table is part of it is hidden, but let's see how you add them. So for instance, if you add t plus s, what will you get? You simply pick elements from t and add them to elements of s. So for instance, if I add 3 plus 4, I will get 7. If I add 6 plus 10, what will I get? What is 6
4.
plus 10? It's 4.
4.
So you realize one thing. Yes, correct. If I pick any element from T and add to an element in S, I get an element in S. And you can check that for all the elements. So we can conclude that T plus S will be equal to S. And then in any case, T is the identity element according to our theorem that we proved earlier. So if you add T to any of these, you will not change them. T plus R will also be equal to R. And you can see the first row here. T plus T is T. T plus S is S, and T plus R is also R, because T is the identity element in this quotient group. So the quotient group consists of these three elements, T, S, and R. We can also check, what if you add S to itself? Simply pick elements from S and add to elements of S. So we can pick, say, what is 1 plus 4? I get 5.
5.
So once you get 5, you don't need to bother adding anymore. You just look to the left coset where 5 is, and that will be your answer. So S plus S will give you R.
R.
So you just need to do one and check where does it fall. So if I add 4 plus 7, I get 11. So I don't need to add anymore. Even if you try the others, you'll get the same. 1 plus 4 gives you 5, and so on. 4 plus 10 will give you 2. So you just need one addition, and then you have your answer. So S plus S will be R. What about R plus R? Just add 2 plus 2, or 2 plus 5, you will get 7. So you can see if you add R to itself, you will get S. So that's a shortcut for adding them. You just do one addition and see where the number falls, and that will be your answer. So the last one is what? S plus R. If you add S to R, what do you get? Let's say 1 plus 2 will give us 3. So S plus R will be T. So that's a shortcut. That's how you make your work easier in computing this. So this gives you the Cayley table, or if you like, you can call it the addition table, because this operation is additive for the quotient group of Z12 by T. So we have done a few examples. I hope this idea of the quotient group makes some sense so far. So now the only thing you need to be careful now is that the elements of your group are now sets. They are not just singletons like we have had earlier. They are complete sets. So this is one element of the quotient group. That's a second element of the quotient group. That's the third element of the quotient group. So the quotient group consists of these three sets, T, S, and R. Any questions? Could you confirm if you can still hear me?
Yes.
Good. So you have some more work to do here. So for the same group Z12, we have picked a different subgroup, which is the subgroup P consisting of these three elements, 0, 4, and 8. So your work is to determine all the left cosets of P in Z12. Of course, P will be a normal subgroup because Z12 is a abelian. Any subgroup of Z12 will be normal. So automatically it will be a normal subgroup. So determine all the left cosets of P in Z12, and also after you are done with that, construct the quotient group of, this should be P, not K. I'm using P here, so I should have P here as well. You can make that correction. So this is a typo. This should be P. So get this quotient group of Z12 by P and work out a multiplication table. So let's see if you have followed. How many elements will this quotient group have?
12.
Pardon? So you are
12.
saying there are 12 distinct left cossets of P in Z12.
No, there are 4.
4.
Okay. You need to understand this carefully. Z12 is the one that has 12 elements. This quotient group is simply the set of all left cossets of K in Z12. So that's what you need to count. You count the number of left cossets. The correct one is actually P, the left cossets of P in Z12. So if you're counting the number of elements in the quotient group, you count the number of left cossets in that group, not the number of elements in the group itself. So any questions? That sounds like a good place to stop, unless you have questions. So you have a bit of work to do. Hope you will find time to do the work.
Excuse.
Yes.
And when we take the subgroup of T to be a subgroup of R to be 0, 2, 4, 6,
R?
and 8 and 10. So now the subgroup.
Yes.
We have the elements like 0, 2, 4, 6, 8, and 10.
What is your question?
And we are told to hapa tunaweka subgroup of T.
What is E?
E in value of subgroup of T.
What is T?
This is the subgroup.
So you want T to be equal to 0, 2, 4, 6, and 8?
8 and 10.
And 10. So how many elements does that subgroup have?
It has 6 elements.
So it has 6 elements. So how many left cossets will it have? How many distinct left cossets will it have?
Only 2.
Yes. So where is the problem?
I was just asking kama tunaweza chukua any subgroup in the Z12.
Yes. In Z12, any subgroup will be a normal subgroup. So this only works if the subgroup is a normal subgroup. So here we are lucky that Z12 is an abelian group. Abelian is another word for commutative. And therefore, any subgroup you pick from there will be a normal subgroup. So unlike the dihedral group, for instance, D3, we know that this is a normal subgroup. H is a normal subgroup. But if you pick the subgroup which consists of only E and B, that is not a normal subgroup. So you can't use that here. So this can only work for, I think this is the only normal subgroup of D3. It doesn't have any other normal subgroup. So you can't set up any other quotient group. This is the only quotient group you can set up for D3. So it's not for all subgroups, it's only for normal subgroups. But if the group itself is abelian, then you're lucky and any subgroup you pick will work because it will be normal. Is your question answered?
Yes.
So have you run out of questions? So I think we'll stop the class there. Those who wish to leave can leave. If you have some questions to ask, you can still hang around and ask.